Then I think we're ready for the next talk. The next talk will be Vladimir Galkin, Professor Galkin, heavy tetraquarks in relativistic quark model. Vladimir, could you show us the slide? Thank you very much.
Do you see me? Huh?
We can see you, we can hear you.
Okay, you hear and see my screen, yes?
Great.
Okay, so first of all, I would like to thank organizers for inviting me to participate in this meeting and to give the talk here. And in this talk, I would like to give a review of the calculations of the masses of heavy tetraquarks in the framework of the relativistic quark model. And this talk was prepared in collaboration with Professor Rudolf Faustov and my student Elena Savchenko. And it is based on the works which are cited here. We see that here are two groups of works. The first one was made quite a while ago and in collaboration with Professor Dietmar Ebert, to whom I'm particularly grateful for. And in this series of papers, we developed the relativistic quark model for description of tetraquarks, and tetraquarks with consisting of two heavy quarks, one heavy quark and light quark were considered. And here in the last paper, which is based on the diploma work of Elena Savchenko, we just applied this model for the consideration of the tetraquarks, which are composed from heavy quark only. Already exotic states were discussed at this conference, and in the following table I just want to show you experimental candidates for the hidden charm exotic mesons, and so in this table they start from famous X3872, which was discovered by Bay Collaboration already more than 17 years ago, and it ends with two states X3800, which was discovered and reported this summer by the LHCb Collaboration in the spectrum of J-psi pairs produced in proton-proton collisions. And this last state, X4740, the evidence for it was presented only last week, also in the paper of the LHCb Collaboration. As we see from this table, for some of the states, the quantum numbers are known. For these states such as Y states, these quantum numbers are just easily determined from the decay process, from the observation process. And for the other states, say for this X3872, a rather complicated angular analysis was necessary in order to determine all this its quantum numbers. Also in this table, there are present the so-called Z states, which are charged. So they are explicitly exotic states because they need to contain an additional pair of light quark and antiquark in order to make these germanium-like states to have charges. Also, there are states which are observed in the phi J-psi mass spectrum, these states, and these states should contain also not hidden charm, but also hidden strangeness. What is the important feature of these states is that most of the states are located close to thresholds of open or hidden flavor meson production. Many theoretical interpretations were put forward for these states. The first one was just a conventional interpretation, so that it's a heavy quarkonium states which are influenced by open flavor thresholds. However, this approach is not applicable for these, say, charged Z states. Also, the exotic interpretation were put forward. That's a molecular interpretation, that it is this state is a loosely bound state consisting from two heavy mesons. They are bound by the exchange of meson, or maybe some van der Waals force which originate from soft gluon exchanges. And so the states should be located very close to the corresponding meson threshold, and it has a rather small binding energy, and thus it has a rather large size. It can reach tens of Fermis. Then interpretation as tetraquarks, it's a tightly bound 4-quark state, which is bound by the colored QCD forces. So it has a usual dimension of hadronic size. Hybrids, which consist from the quark-antiquark pair and gluon with excited gluonic degrees of freedom. Hydroquarkonium is a compact quarkonium state, which is embedded in excited light quark matter. And also some of the states were interpreted as just pure kinematic or scattering effects at its corresponding thresholds. In this talk, I will just discuss this tetraquarks in diquark-antidiquark picture, and our main assumption will be that the tetraquark is a bound state of diquark and antidiquark, which are in color anti-triplet and color triplet configurations, and they are bound by the strong colored forces. Thus, we reduce a very complicated body relativistic problem to solutions of two significantly more simple two-body problems. So first we consider diquark as a bound state of two quarks, and then we consider a tetraquark as a bound state of diquark and antidiquark, and we assume here that diquarks interact as a whole, so there is no separate interactions between quarks and antiquarks from diquark and antidiquark respectively. Such tetraquarks should have typical hadronic size, and we expect rich spectroscopy, since radial and orbital excitation can exist between diquarks. When considering diquarks, it's very important to take into account that diquark is a composite quark-quark system. So diquark is not a point-like object. It's important to take into account its size. And it can be taken through the introduction and calculation of the form factor of gluon diquark interaction. And this form factor can be expressed through the overlap integral of diquark wave functions. Also, it's necessary to take into account a Pauli principle that for ground state of diquarks, we can have both scalar and axial vector diquarks if the quarks in diquark are different, but for the same flavor quarks, we can have only axial vector diquarks. And in our calculations, we will consider both light and heavy quarks and diquarks consistently relativistically. So we will not employ non-relativistic view of the expansion. We will consider the heavy tetraquarks with hidden Chaman bottom. Also, we'll consider the doubly heavy tetraquarks with open Chaman bottom. These are explicitly exotic states with heavy quark flavor equals to 2, so their observation would be a direct proof of the existence of multi-quark states. Then we also consider tetraquarks with open Chaman bottom, and will end by consideration of tetraquarks which are composed from heavy quark only. Here it's interesting to consider such tetraquarks since new structures were observed in double gypsy spectrum by LHCb, and also it's also necessary to interpret the absence of narrow structure in epsilon pair production, which was reported by CMS and LHCb collaboration. And we will consider such tetraquarks as the bound system of the doubly heavy diquark and doubly heavy anti-diquark. And to achieve this goal, we will use relativistic quark model, which is based on the quasipotential approach, and diquark as a bound system of two quarks and tetraquarks, and as a bound system of diquark and antidiquark, is described by the quasipotential equation, which is presented here in the Schrödinger-like form. And although it resembles just usual Schrödinger equation, it's significantly more complicated. It contains relativistic kinematics, which is in the left-hand side. Here we see that there is a very non-trivial dependence on the bound state mass, which enters through the relativistic reduced mass here, and the on-mass shell relative momentum B here. And the relativistic dynamics is in the right-hand side. Here we have the quasipotential of the interaction, and it is necessary to construct it, and it is constructed from the with the help of the off-mass shell scattering amplitude. And first, we develop our model for the description of ordinary hadrons, mesons, and baryons, and we will keep all the assumptions from these sectors. So when, as well as the parameters of the model, when we were considering the quasi-potential of the quark-antiquark interaction in meson, we assume that it consists from the potential of the van-Gluon exchange, which dominates at short distances, it's given here, and also the long-range confining interaction potential, which is the sum of the long-range vector and scalar confining interactions. Moreover, we assume that the vertex of the long-range vector interaction contains not only Dirac path, but also the Pauli term. Here, U is Dirac bispinors, and here we have the Dirac matrices. Thus, this potential contains both spin-independent and spin-dependent relativistic contributions. In the non-relativistic limit, the confining interaction resumed to the reduced to the following form. Here, epsilon is the mixing parameter of the vector and scalar confining interaction, and in the sum, it reproduces the linearly rising potential. Thus, in non-relativistic limit, our quasi-potential reduces to the usual Cornell potential. Thus, it can be viewed as a relativistic generalization of this Cornell potential. As I already said, all parameters of the model were fixed from meson masses and radiative decays, and quark masses and parameters of the potential have rather standard model for quark models. And since we consider also light quark, we use this expression for the running coupling constant alpha s with freezing. And the most maybe interesting parameters here are our new parameters. It's epsilon and kappa. It's the mixing coefficients of vector and scalar confining interaction and long-range anomalous chromomagnetic quark moment. And their values were fixed to -1. The value of epsilon was fixed from the heavy quarkonium radiative decays, such as J psi to eta C plus gamma, and these decays are very sensitive to the Lorentz structure of the confining interaction. And this value of kappa was fixed from the fine splitting of triplet p levels of heavy quarkonia. And then the same values of epsilon and kappa were obtained when we compared the heavy quark expansion in the frame of work of our quark model with model-independent predictions of the heavy quark effective theory. Let me note that for the chosen value of anomalous chromomagnetic quark moment, long-range chromomagnetic interaction, the long-range chromomagnetic interaction, which is proportional to 1 plus kappa, just vanishes. And this is in accord with the flux tube model. Now we apply the same approach to the consideration of the tetraquarks. First, we consider the quark-quark interaction in the diquark, and here we use just the standard rule that it is 1/2 of the quark-antiquark interaction. So here there is the corresponding quasipotential. And for diquark anti-diquark interaction, we also use the same assumptions, because we assume that again it's composed from the potential of the one gluon exchange, which dominates at small distances, and the long range confining interaction, which again is a mixture of vector and scalar pieces. However, here it's important to take into account that diquarks have integer spin, so there are some modifications. They are just written on this page. This, the effective long range vectors, vertex of the diquark interaction and the diquark wave functions. Here it's also important to note that we do not consider diquark to be a point-like particles. So here there is additional contributions, which are the matrix element for the vertex of diquark-gluon interaction between diquark wave functions. And this vertex in quasipotential approach can be calculated through the overlap of the diquark wave functions. And here gamma here is a two-particle vertex function. On this figure is shown in the impulse approximation. And as a result, a form factor of the diquark appears in the calculations. Using such approach, we calculated the masses of the light diquarks. They are just given in this table, and we compared them with the other theoretical predictions in different approaches. Non-Baryon linear model, different versions of beta-salpeter equation, quench lattice calculation, and we find that there is a good agreement between these different theoretical approaches about the light diquark masses. Here in this table, I also give the masses of heavy light and doubly heavy diquark masses. Now we use the calculated wave functions of diquark to calculate the form factor of the diquark-gluon interaction, and it's here shown for light diquarks and heavy light diquarks. And such behavior of the form factor is rather easy to understand intuitively. When we are far away from the diquark, say at distances larger than 1/2 of Fermi, we cannot resolve its structure. So it's look like a point-like. So we have the form factor which is equal to 1. When we approach the diquark, we start to resolve more and more of its structure. And when we are in the center of mass of the diquark, then this interaction vanishes. On this transparency, I just show the diquark anti-diquark interaction quasipotential. It's rather complicated. It contains spin-independent terms and also spin orbit contributions. We had different ones, and tensor term and spin-spin term. And here it's important to show that that this one gluon exchange interaction, which leads to the Coulomb potential, now contains additional form factors of the diquark and anti-diquark, which take effectively their sizes into account. Now we can substitute this equation, this quasipotential in the quasipotential equation and solve it numerically and obtain the masses of the tetraquarks. In the following table, I just present the ground state masses of the hidden champ tetraquarks. Here I give their quantum numbers, their diquark content. S stands for the scalar diquark, A for the XL vector diquark. Here we give just for the champ tetraquarks, tetraquarks with hidden champ and strangeness, and tetraquarks with with hidden champ and open strangeness. And as we see here that for the state 1++, we get the prediction of the mass 3871, which is very close to the corresponding thresholds, which are given here in this table, and just almost coincide with the mass of the famous X3872. And now we can also calculate the excited states. It's 1p excited state, 2s excited states, and 1d, 2p states. Their prediction for their masses are given in these tables. The same calculation can also be performed for the hidden bottom tetraquark states. Here we give our prediction for the ground states, and if we compare to the corresponding thresholds, we will see that all the states are located just below the thresholds for the decay in the 2B mesons. Now let us confront our predictions and find with experimental data and find for them possible experimental candidates. And we see, and I already said to you, we have a good candidate for X3872. Also, we have good candidates for charged these C states, for Y states, vector states. Here, Y states are just p-wave excitations, which composed either from two scalar diquarks or two axial diquarks. And also, we have 4 candidates for the states which with hidden charm and hidden strangeness. This one, this one, this one, and this one. And this one is just was the evidence for it was just presented last week, and we see that here we have a good candidate. And of course, if this state is different from the previously observed X4700. Now it's also necessary to mention that we do not have candidates for this charged these states, which are probably hydrogermanium state, and we do not also have the candidates for charged bottom tetraquarks, which are probably molecular state. And in this table, we also give the bottom counterparts of the corresponding charmed tetraquark. Now we can go to the doubly heavy tetraquarks with open charm and bottom. They contain just two heavy quarks and light antidiquark. Here we give the predictions for when both heavy quarks are C quarks. Here both quarks are B quarks, and here one quark is C and another B quark. Here we give the quantum numbers, the predicted masses here given, and also T is the threshold, the lowest threshold for decay into two heavy light mesons, and delta is the difference between the mass and corresponding threshold. So if this value is negative, then corresponding tetraquark should be a narrow state, which cannot decay into two heavy light mesons due to quark rearrangement. And we see that this delta is negative only for the tetraquark, which is composed from two big quarks and light diquark. However, for the states which where delta is rather small, corresponding state can be observed as resonances since their decay due to rearrangement will be suppressed kinematically due to the phase space. Now we can do the similar calculations for the open charm and bottom systems. Of course, there are two thresholds. One threshold is to decay to two heavy light mesons, and the other threshold to decay to be C meson and a light meson. Of course, the second threshold is lower. However, such decays are suppressed by the heavy quark spin symmetry. So maybe some of the corresponding tetraquarks can be also narrow. Now we go to the last topic, is the tetraquark, which is composed from 4 heavy quarks. Here in the following table, we give our predictions for the fully charmed and fully bottom tetraquarks. Of course, they should consist from XL vector diquark and XL vector antidiquark. Here we give the quantum numbers, the predicted masses, the thresholds, and the values of the threshold mass, and also the difference between the mass and corresponding threshold. And as we see from this table, all the predicted masses of such tetraquarks are located just significantly higher than the lowest thresholds. And especially for this fully bottom tetraquarks. And this is related, so here we have the difference between the mass of the fully bottom tetraquark threshold of about 400 or 500 MeV. So it's approximately a factor of 2.5 larger than corresponding difference for the full charm tetraquarks. And this is the result of the considering diquarks to be not a point-like object, since here the fully bottom tetraquarks is significantly more compact state. Thus, here the size of the tetraquark and the form factor which suppresses the one-gluon exchange is significantly more important than in the case of the fully charmed tetraquarks. Also, this influences the mass splittings, spin splittings corresponding. We see that they are significantly less here than in the fully charmed tetraquark state. So as a result, we see that here we have a big phase space for rearrangement decays of such tetraquarks into two botamonia. And this can explain why there is no narrow states observed by the LHCb and CMS collaboration in double epsilon production spectra. And this also result is consistent with calculations on the lattice, which say that there are no fully bottom tetraquarks below this, the thresholds of the decays for 2 quarkonium states. These results were obtained in the beginning of this year, and they were included in the diploma work of the Elena Savchenko, which was defended in May this year. And the summer LHCb Collaboration published their data, and they observed a narrow structure here, which is around 6.9 GeV, which is matching the line shape of resonance. They called it X3900. And there is also a broad structure here, which is about twice the mass of the J psi. And they also say that in the same mass region, also some more resonances can present. So here can be another resonance located here. And as we see from this table, that this broad structure is a very good agreement with our prediction for this tensor 2++ state, which is just located over here. Now we are just calculating the masses of excited, all charm tetraquarks. Now the calculation is in progress, so I will just give you all the preliminary results. So we calculated the masses for first orbital excitation, first radial excitation, and second orbital excitation. And as we see, here is a good agreement of these states which are just shown in green with the masses which were measured for this X6900 state by LHCb collaboration. There is a little bit difference of the masses, which is the result of the different data analysis. Here, there is no interference with a non-resonance single proton continuum, and here there is with interference. So it can be also the 2++ first radially excited state, and can be also 2++ or 0++ state of the second radially excited state. And although these states have a rather large phase space for decay to germanium states, such decays could be suppressed due to the fact that here it's just we have a non-trivial knot structure for this first radial excited state, and in the case of orbital excitation, it is necessary to overcome the centrifugal barrier. Also other masses of tetraquarks composed only from heavy quarks were calculated. The ground states, this is masses, there is corresponding thresholds, and all these states are found just above these thresholds, and also for different tetraquark compositions. Now I come to my conclusions. So in the talk, we just presented the calculations of masses of tetraquarks with heavy quarks, and they were calculated in the diquark-antidiquark picture. We use the dynamical approach, which is based on the relativistic quark model, where both diquarks and tetraquarks masses were obtained by numerical solution of the quasipotential equation with corresponding relativistic potentials. The size of the diquark was taken into account. We do not have any free adjustable parameters in this approach, and it was found that the following masses are compatible with the masses of the hidden champ tetraquarks with corresponding quantum numbers. And it's important to note that most of these experimental states were observed after our predictions. We've also found that the ground states of the tetraquarks with hidden bottom have masses below the open bottom thresholds, and thus they should be narrow. We do not have tetraquark candidates for this charged ZB tetraquarks, and probably they are molecular states. We're also given the prediction for the masses of the bottom counterparts of the champ tetraquark candidates, and considered the tetraquarks composed from two heavy C quarks and light antidiquark, and their predicted masses are above the open champ thresholds. So these tetraquarks could be seen only as resonances. Only for this state 1+ state of tetraquarks composed from two bottom quarks and light antidiquark is found to be below the corresponding B to a threshold. So the state should be narrow. We considered the ground states of fully heavy tetraquarks, and all their masses are found above the threshold to decay of two heavy quarkonia. So such tetraquarks can be observed only as broad structures decaying dominantly to quarkonia. And the broad structure recently observed by the LHCb collaboration in the mass spectrum of the J-psi pair can correspond to the tensor tetraquark state. And the narrow the state X6900 could be its first radial or second orbital excited states. And all the ground state fully bottom tetraquarks have masses significantly higher than corresponding thresholds, and thus they're expected to be very broad. And this is in accord with the absence of the narrow, beautiful tetraquarks in the epsilon pair production reported by the CMS and LHCb collaborations. So that's all. Thank you.
Okay, thank you very much for a nice talk. I think we have some questions now, and I think Kazem Azizi was first who raised the hand. So, any questions?
Thank you very much. Professor Galkin, thank you very much for the very nice talk. I have a small question. In the numerical analysis, you the bottom and one quark masses assented in the PG in 1 GeV scale. For the strange and uptown quarks use very high values for their mass. How do your results depend on the light quark masses, strange or uptown?
You mean in our approach, unfortunately, it's very, I couldn't hear you properly, but as I understand, you say what is the dependence of our light quark masses, yes, of our results. In our model, we use is constituent quark model, exactly. So we do not use the current quark masses, we use the constituent quark masses, which are given here. And of course, it's also with these quark masses were fixed from the consideration of light meson spectra. And with these masses, we can reproduce even raw meson. If we just consider relativistic contributions not non-perturbatively. It's very important because then we can just, then the mass of the light, say, pi meson enters in the denominator of this spin-spin interaction. And that's why it produces the large splitting between the rho and, for say, example, and pi meson.
Thank you very much. I understand.
May I ask a question?
Yeah, of course, yeah.
Please, Vladimir, in your approach, in the presented approach, the notion of a diquark plays an essential role. Is there any signs maybe coming from, say, latest calculations? Is there something which supports the notion of the quark coming from TCB itself, say, in the latest?
I think that there are a lot of evidence for possible existence of diquarks, which come from different approaches and maybe from experiment. For example, if we consider the baryon mass spectra and consider the baryon as a 3-quark state, then we will have quite a lot of excitations because we have a lot of degrees of freedom. And experimentally, not so much states are observed. And if we introduce the diquarks, then we just freeze some of these degrees of freedom, and the number of the excited states is significantly reduced. And also diquarks, I think it's very important also in other areas of physics, and so even okay.
Yes, I agree that it perfectly works. That's clear. But I mean, I remember that some calculations were made within the lattice QCD, and they also showed something.
Yes, in some lattice calculations also diquarks appear. And for example, in this table, we just give maybe rather old but quenched lattice calculations will also have their calculations of the diquark masses. Of course, diquark is not cannot be considered as some real system because it has a color.
Yes,
it's unobservable, of course, but you can speak about correlations, diquark correlations.
yes, right. Clear. Thank you very much.
I have also a question.
Yes, my hand is raised already a long time. Petrov asking. The question is, why don't you consider the light, total light, tetraquarks and pentaquarks and maybe other configurations? Is there some technical obstacle, or there is a kind of probable principle?
No. There is no problem for considering light tetraquarks. As I already said, maybe on this beginning slide, we also considered light tetraquarks in our approach and calculated their spectra. I think it's published maybe in this paper. And there is a good agreement for this. We can interpret lightest scalar mesons as tetraquarks.
Okay.
So there is no problem. For pentaquarks, maybe it's a little bit more difficult since we have 5 quarks. And it depends how we can consider if 2 diquarks, one antiquark, or say maybe 1 baryon and maybe meson.
What is the scale of the masses of these light many-quark states?
Light, for example, if the lightest scalar state is just about sigma meson.
Oh, 4 quarks?
Yes, yeah.
Very nice, huh? Thank you.
And this is related just to treating the relativistic effects non-perturbatively. So if you treat them perturbatively, then you will not get such smaller masses.
Yes, sure.
It's the same as for pion. You will not get a pion mass correctly if you do not treat relativistic effects non-perturbatively.
Thank you.
Important feature.
I have also a question. It concerns the BB anti-light states you investigated. Could you perhaps go to the table? As far as I saw it, you investigate 4 different states.
This one, yeah, this table, yeah.
Yes, so the upper block, you have 4 states, the middle column. So my question is, why don't you investigate the JP1 minus state, at least from lattice QCD combined with Born-Oppenheimer? This is the next promising state with respect to being bound, or a rather clear resonance in addition to what you marked in blue.
Okay, thank you, Mark. In fact, we calculated only the ground states. And the ground states have these quantum numbers, and that's it. In order to consider 1 minus state, it's necessary to consider the excitation between diquarks. And the mass will be larger, but probably it's just below the corresponding threshold. We have not done such calculation.
I don't think it's below, but at least it's very close to threshold.
Maybe it's very close. Yeah, but
was interested whether there's a physics reason why you don't think this is not going to exist, or a technical reason?
No. We do not have any physical reason or maybe technical reason. In principle, it's possible just to calculate, but we have not done it yet. Thank you for your suggestion. Probably we will just do such calculations. Okay, thank you.
Okay, thank you very much for the question.